Hello, my name is Hantian Zhang, and I am a fourth-year PhD student at Georgia Tech. Together with Hyun from KAIST, we are going to present our paper, iFlipper, Label Flipping for Individual Fairness. This work is done together with Jaeyoung Park, Xu Chu, and Stephen Whang. Nowadays, machine learning and AI algorithms are used for making high-stakes decisions that will have a big impact on our lives. For example, Amazon is accused of using gender-biased AI tools that filter out more women's resumes, which should definitely be avoided. It is of vital importance that we make sure that the machine learning models are created and used responsibly, and fairness is one important topic that this paper will focus on. There are different definitions of what fairness is, and in this paper, we focus on the notion of individual fairness, that is, similar individuals should get similar outcomes. In practice, how to define similarity is tricky, and there isn't an universally adopted definition. In this paper, we use Euclidean distance between two data points to measure similarity. Also, we focus on binary classification problems. Now, let's look at the following example. Assume we have the following resumes to train an AI recruiting model. Each resume has two features, gender and score. Now we define that if the score difference is at most 10, then we think the two resumes are similar and should get the same result. If the algorithm decides to hire the first 3 people and reject the last 2 people, similar people are accepted or rejected at the same time, then this classifier is individually fair. However, in practice, we find that training with biased data may result in an unfair model. For example, due to some historical bias, a female applicant was rejected incorrectly, and the data is also used to train the machine learning model. This will potentially lead the model to reject more women and amplify the historical bias. We need to fix this problem. Our approach is to fix the training data to make it more individually fair by flipping the labels. Recall that individual fairness says that similar people should be treated similarly, and the violation would be that 2 similar people get different outcomes. In this example, we have defined that if the score difference is at most 10, then they are similar. So the first 3 resumes are similar to each other, but the third one has a different outcome than the other 2, causing 2 violations, one between resume 1 and 3, and the other between resume 2 and 3. We can solve this problem by flipping the label of the third resume to accept. This will reduce the number of violations to 0 in the data, and training the model using the fixed data will lead to a more individually fair model. However, this does come at the cost of sacrificing accuracy. As we flip more labels, we can reduce the number of violations and increase individual fairness. However, this means that the model is trained on a different distribution than the original training distribution. The more labels we flip, the further the distribution is and the worse the accuracy could be. As an extreme example, if we simply flip all labels to be 0, the trained model is indeed individually fair because everyone is getting the same outcome, regardless of if they're similar or not, but it is not going to be useful at all. Here, if we look at the figure, the x-axis is accuracy, the higher the better, and the y-axis is consistency score. The higher the consistency score, the better the individual fairness. We can see that there's a trade-off between fairness and accuracy. So we formulate this as an optimization problem. We want to flip the least number of points to ensure high accuracy with the constraint that the total number of violations is below a certain threshold M to ensure high individual fairness. Let's take a closer look at the optimization formulation. This is an integer programming problem as we focus on binary classification and the labels could only be 0 or 1. Here, y is the new label for data point I and y prime is the old label for data point I. If y is different from y prime, then it is a flip. The objective is to minimize the total number of flips. Now let's take a look at the constraints. Here, wij is the similarity between point I and point j. If wij equals to 1, it means that point I and point j are similar. If point I and point j are similar but have different labels, then it is a violation. And the constraint is that the total number of violations is at most n. If the fairness constraint is satisfied by a set of new labels, then we call them a feasible solution. Note that as long as m is greater than or equal to 0, we can always find a feasible solution by making all new labels the same. An optimal solution is a feasible solution with the minimum number of flips. In the paper, we proved that this problem is NP hard, and we need some scalable approximate algorithm to get a good result in a short time. A simple solution is the greedy algorithm. The algorithm counts the number of violations that can be reduced by flipping each point, and flip the point with the highest reduction each round. However, the greedy algorithm may fail to find a feasible solution, even if there exists one. Also, in the paper, we considered gradient-based algorithms and clustering-based algorithms, and they all can fail to find a feasible and near-optimal solution. iFlipper solves this problem by first relaxing the integer programming into a linear programming problem, which can be solved efficiently by a state-of-the-art solver. The solver will find a feasible and optimal solution. However, the solution cannot be directly used to train a binary classification model because they can contain continuous values and we need the labels to be binary. So we need to run the linear programming solution while guaranteeing that after the rounding process, the solution is still feasible and near optimal. To solve this problem, we develop an adaptive rounding algorithm that rounds the optimal solution of the linear programming to integers, with the guarantee that the rounded solution would also be feasible and have a bound on the optimality gap. We further develop a reverse greedy algorithm to further reduce the number of flips after adaptive rounding. Now, Hyun will take over and talk about more details.
Hi, I'm Hyun, and I will continue to explain iFlipper in detail. The first part is a linear programming relaxation, which can be done in 2 steps. We first replace the square term in the original equation to an absolute term. We then convert it to an integer linear programming problem by replacing each absolute term with an XOR expression, a variable z, which can be expressed as 4 linear constraints. This is possible because all variables are binary. We then relax the problem to an approximate linear programming problem by replacing integer constraints with range constraints. Now, all variables and constraints are linear, and this relaxation allows us to solve the problem efficiently by any off-the-shelf solver. However, the optimal solution of the LP problem cannot be used because of the continuous values. Suppose we have the following graph in the bottom left figure, where black color indicates label 1, white color indicates label 0, and similar nodes are connected by edges. Here, there are 4 violations among the node pairs. Let's say we want the number of violations to be at most 2. In this case, solving the LP problem can produce an optimal solution as in the bottom right, where the 2 labels with value 1 are flipped to 0.5, such that the total violations becomes exactly 2, while the labels are minimally flipped. In the end, we want to make these labels 0 or 1. A simple method is to round the continuous values to their nearest integers. However, this method does not guarantee a feasible solution, which means that the solution may not satisfy the violation limit. In our example, if we round the 2 0.5s back to 1s, the total violations becomes 4 again. Now, I will explain how we can do better than simple rounding. Our approach is based on a surprising key observation that any LP optimal solution can be converted to another optimal solution where it only has 0, 1, or a unique alpha value that is between 0 and 1. For example, the bottom left figure shows one instance of an optimal solution where it has values of 0, 0.8, and 0.2. This solution can be converted to another optimal solution in the right figure, where there's only one non-zero one value that is 0.5, while having the same number of flips and total violations. We prove why this kind of conversion is always possible in our paper. Knowing that there are only 3 possible label values allow us to propose an adaptive rounding algorithm that is much better than simple rounding. The crux of the algorithm is to round the alpha value to 1 if there are more edges between 1 and alpha nodes than between 0 and alpha nodes, and otherwise round it to 0. In our example below on the left, there are only 0 and 0.5 pairs, which means adaptive rounding will round alpha value to 0 as shown on the right-hand side. Our algorithm has theoretical guarantees in terms of optimality, where the number of flips it performs compared to the minimum possible number of flips is bounded by a linear function on the number of minimum flips and the alpha value as shown in the below equations. Please refer to our paper for details. So, we developed an algorithm called reverse greedy to further optimize a solution, which unflips flipped labels as long as the total violations does not exceed the limit. Continuing from the left figure, we unflip the first node from 0 to 1, such that the final solution has fewer flips and still satisfies the violation constraint. In our experiments, we use 3 benchmark fairness datasets and 1 synthetic dataset. We evaluate our method using model accuracy, individual fairness, and running time. To measure fairness, we use a consistency score that measures the similarities of model predictions between similar data points. If all similar data points have the same model predictions as well, there are no violations, and the consistency score is 1. The figure shows fairness and accuracy trade-off results with logistic regression models on COMPASS dataset, where the x-axis is the test accuracy and the y-axis is the test consistency score. Again, higher values are better. Here, original is where we train a model on the original data. In the figure, we compare iFlipper with 3 state-of-the-art pre-processing baselines, which do fair representation learning instead of flipping labels. As a result, iFlipper outperforms baselines in terms of consistency score and accuracy. Finally, we compare the runtimes of iFlipper with the other baselines in the table. As a result, iFlipper is significantly faster than LFR and iFair on all the datasets. While PFR is the fastest, the results are not meaningful as it has much worse accuracy and fairness than iFlipper. To conclude the talk, we propose iFlipper, which minimally flips labels into training data to improve individual fairness. We first propose a label flipping optimization problem, which is NP hard. iFlipper solved this problem efficiently by solving an approximate LP algorithm and rounding the solution such that it is feasible and also has theoretical optimality guarantees. We demonstrate on real data sets that iFlipper outperforms other baselines in terms of fairness, accuracy trade-off, and running time. Thank you for listening to our talk.